So my name is Ellie Grigsby. I'm one of the deputy directors here at ICERM. So ICERM stands for the Institute for Computational and Experimental Research Mathematics, and we're affiliated with Brown University. Our core funding is through the National Science Foundation, the Federal National Science Foundation. We have additional support from the Simons Foundation and Microsoft and other places. Our mission is to promote positive interaction between mathematics and computation. So algorithms and software as a byproduct and outcome of mathematical research, and also using computer experiments as a testing ground for mathematical hypotheses and everything that we do. So we are so pleased to welcome Steven Strogatz as our guest speaker tonight, and I know you guys are excited too, so I'm not going to spend a lot of time blathering up here beforehand, but I will spend a few minutes saying some great things about Steven Strogatz so you can get excited. So he studied mathematics at Princeton, Cambridge, and Harvard, and taught at MIT before moving to Cornell in 1994. You may have read his math blogs for the New York Times and the New Yorker, or heard him during one of his frequent guest appearances on Radiolab or Science Friday. He's received many numerous honors, including MIT's and Cornell's highest teaching prizes, a Lifetime Achievement Award for the communication of math to the general public, the Lewis Thomas Prize for writing about science, and membership in the American Academy of Arts and Sciences. He's also, in his spare time, written a number of books, Nonlinear Dynamics and Chaos, Sync, The Calculus of Friendship, The Joy of X, and most recently, Infinite Powers, on which this talk will be based. And as an added note, right after the talk, Steven will be spending a little bit of time signing copies of that book outside, and there will also be books available for purchase if you're interested in that. So without further ado, thank you very much to Steven for giving us this talk.
All right. Hi, everybody. Thank you very much for coming out, and thanks for the nice introduction, Ellie. It's great to see lots of young people here. I've got students, and looks like even maybe some parents bringing their kids. That's all good. So you've come out to hear a talk. What's the big deal about calculus? I'm going to be approaching the answer to that as an applied mathematician. I could answer it as a pure mathematician, too. I mean, within math itself, calculus is a big deal. But let me focus instead on why is it a big deal for the world? What does it do for us? You know, there are so many things that calculus does that are unsung. It's like in the background. You don't even realize how much of your life depends on calculus nowadays. For instance, without calculus, we wouldn't have radio, we wouldn't have television, microwave ovens. We wouldn't have been able to put astronauts on the moon. We wouldn't have unraveled the human genome. So I'm going to give you a whole big list of these kinds of things. And at the end, if you're curious about, you know, like, what's the evidence for what you said about the human genome or about the astronauts, I'll be happy to talk about that. But let me just blast through these for now. I mean, it's not like it's all for the good. We wouldn't have nuclear energy, but we also wouldn't have nuclear weapons. So like anything in science or math, it can be used for good or evil purposes, and calculus is no exception there. We wouldn't have ultrasound for expectant mothers. We wouldn't have GPS for lost travelers. It's everywhere. I would even claim that without calculus, we might not have the Declaration of Independence. Now, that one I realize is not an obvious connection, so I will be happy to take a question at the end, like, what? What do you have in mind there? I do have something in mind, so I'll try to make that case if you're curious. Okay, but so you get the main point here, that I'm claiming that calculus helped make the world modern. And that's a little bit surprising in a way, because, you know, especially if you've taken calculus, which I'm guessing some or many of you have, though I don't assume that you have. I mean, you don't have to for this talk. I'm aiming at a very general audience here. But for those who have seen calculus, you know, it seems like a lot of arcane formulas about areas under curves and slopes of curves. And you might think, well, what does this have to do with the Declaration of Independence or GPS or ultrasound? It's a very far-fetched claim. And I'm making this much bigger claim that calculus, which began as an outgrowth of geometry and was about shapes, has helped to reshape civilization. And so that is a puzzle. How is that possible? How could it have come so far? And so I hope by the end you'll see, you know, the journey that calculus made. So I want to try to embody the story with this, by beginning with the story of two men. One of them is this gentleman, Herman Wouk, who is still alive. He's 103 years old now. This is a picture from him around the time of World War II. He's a writer from my parents' generation, actually, and was known as one of the great chroniclers of World War II. You may know some of his books. One of the most famous is The Caine Mutiny, made into a movie with Humphrey Bogart. He won the Pulitzer Prize for that book. But he also wrote some books that, actually he had intended to write one big book about World War II. He was in the war, in the Navy. And it ended up ballooning into two big books that came to be called The War in Remembrance and Winds of War. They're big bestsellers. Anyway, so while he was doing research for those books, he wanted to learn a little bit about the scientists who had worked on the building of the atomic bomb. Because that was a time in the world's history when science started to seem to be very important. You know, it could win a war, it could end a war, it could kill hundreds of thousands of people in an instant. Science had to be taken seriously in a way that it never had before, especially physics. So as part of his story about World War II, he asked, where could I meet some of the physicists who built the bomb? And he was told maybe a good place to go would be Caltech. So he went out to the California Institute of Technology and was told, there's a person you should talk to named Richard Feynman. He's difficult, but very brilliant, and you'll have a good time talking to him. And so here's Richard Feynman teaching his students at Caltech. And he was a joker. Some of you will know his books, his escapades. He wrote, or books were written. I mean, he loved to tell stories about himself. And those stories often cast him as sort of the, you know, every man who outsmarts all the smarty pantses. So here he is playing bongos. He would break into safes when he was working at Los Alamos, steal government secrets, you know, all kinds of, he thought he was being Mr. Funny Guy. So that's his character, the rascal genius. And so there's Herman Wouk interviewing Feynman, and they're talking, and they pretty quickly realize that they have things in common. They're both Jewish guys, they were both in the war. They're not on common ground with religion. Feynman is quite an atheist, extreme, and Wouk is a devout Orthodox Jew. But they're both Jewish, and anyway, they start kibitzing about all that, and their times in New York together. And so they have a good time, and after they're done talking, as Wouk is leaving, Feynman says, I have to ask you one thing, though, before you go. Do you know calculus? And Wouk, as I say, is a novelist. He admits, no, actually, I don't. And Feynman said, well, you better learn it. It's the language God talks. And that made a big impression on Herman Wouk. The language God talks. Calculus is the language that God talks. What could that possibly mean? He wrote a book with that title. He was so struck by this remark of Feynman, this quip. And he became friends with Feynman, and they spoke many times over the years about the tension and some of the common ground between religion and science. You may see that if you can read it back there, the subtitle, On Science and Religion. So if you're interested in this question of the tension and possible reconciliation between science and religion, this could be a book for you to look at. Wouk also discusses some conversations he had with other prominent atheists, Steven Weinberg, a Nobel-winning physicist, and other interesting people. But anyway, so as to the question of did Herman Wouk know calculus? No, he didn't. And after he felt a little bit maybe embarrassed or something by Feynman's comment, he thought maybe he should learn it, especially if it's the language God talks. And he's interested in God, very seriously interested. So he tells the story of his attempt to learn calculus. In the book, he mentions it. He says, I picked up and skimmed freshman texts in college bookstores, hoping to come across one that might help a mathematical ignoramus like me, who had spent his college years in the humanities, i.e. literature and philosophy, in an adolescent quest for the meaning of existence. Little knowing that calculus, which I had heard of as a difficult bore leading nowhere, was the language God talks. So he goes on this quest. He's going to try to learn the language of God, and it's not easy. He reads the freshman texts. They don't help. You probably know some of these books. He picks up a book with a very attractive title, Calculus Made Easy. That's actually quite a famous book, and it's a good book from the early 1900s. And but that he found impenetrable too, with his background. Just couldn't make heads or tails of it. He hired a tutor, a math tutor, an Israeli guy, who he figured he could learn a little spoken Hebrew on the side and calculus too. Didn't work out. He signed up for a high school course and would go with the 18-year-olds. And after a few months, he fell behind and he had to give up. And as he was walking out, the students clapped for him on the way out. And he said it reminded him of showbiz, where they have the concept of sympathy applause for a pitiful act. So he had a very hard time learning calculus. And I'm telling you all this because I think of Hermann Wouk as a metaphor for the reader that I'm trying to reach. There are people out there who would like to understand what calculus is. They're curious, they've heard about it. They're a person of goodwill, good intelligence, curiosity, creativity, but they just don't have the math background to follow it. And so I'm aiming what I'm going to talk about today at them. So if you're a professional mathematician, you may wonder, I thought this was going to be a talk about calculus. It's not going to be that kind of talk about calculus. It's going to be talking to Hermann Wouk. Actually, I sent a copy of my book to Hermann Wouk. I've never met him. His wife passed away recently. They had a long, loving marriage, but he's very old. As I say, he's 103. He's in a home. I was able to find his agent's address, and I hope the book has gotten to him. And I, in the book, say, this one's for you, Mr. Wouk. I hope that he'll look at it if he's still interested in calculus. I don't know if he is or if he even received the book or what, but okay. So anyway, that's the book, Infinite Powers. And I think maybe my first point should be, well, what could Feynman have meant with that remark? The language God talks. What might he have had in mind? You know, it's a pretty provocative comment. And so let me try to illustrate it with take it down to earth a bit. I want to tell you some stories about an example of God's language in action. And it has to do with the story of electricity and magnetism and what we learned about them with calculus and how what we learned did change the world. So it's a case study in my larger theme. And so let me begin with electricity. You know, you're all familiar with electricity. There's the electricity you can plug into in the wall, but you know, you may have played around with static electricity. This is my daughter, Leah, when she was young, on her grandmother's bed. She'd been fooling around in the apartment, and her hair, it was the winter, you know, I mean, you can see, you know what I'm talking about. Her hair got very staticky and did that crazy thing, and I took a picture of it. So there's static electricity, and people around the world had known about static electricity for, I don't know, certainly centuries, maybe millennia, without really understanding what's causing phenomena like that. And also there are these other kind of puzzling phenomena having to do with magnets. Right? As little kids, we like to play with magnets. They could repel each other or attract each other. And they have this amazing property that if you put a magnet on a piece of paper and then sprinkle so-called iron filings, I don't know if anyone does this anymore. Probably everyone's just looking at their iPhones. But I mean, back in the day, when people used to play with chemistry sets and physical things, is that right? I don't know. Do kids play with magnets anymore? Does anyone even know what iron? Okay, I have a perfect specimen right here in the front row. You have played with magnets? Did your mom let you sprinkle iron filings around, like these little, because you know, you could eat them, or it could be bad. Maybe you're not allowed to do that anymore. But so, okay, there are these little little slivers of iron that if you sprinkle them around and then jiggle the paper, they make this kind of amazing pattern that you're seeing around the magnet. And what it's taken to mean is it shows you what we call the field lines around the magnet. There's this invisible field of force that can be visualized through the pattern of these iron filings. And so when people in the 1800s tried to understand what was going on with electricity and magnetism, they started to think about these invisible fields of magnetic fields and electric fields and how they interact. And so various laws were discovered, which you could learn about if you take a freshman physics course. I won't go into those. But those laws were later encapsulated in beautiful equations by this gentleman, James Clerk Maxwell, who is a Scottish physicist in the mid-1800s, around the time of, say, the US Civil War. He's a young man in that picture. If you know Maxwell, you know, from other pictures, he's usually shown as an old man with a big beard. But this is the young Maxwell. And he realized that calculus gave a perfect description for all these various laws that had been discovered about the way magnets and electricity worked, that it was a perfect language for describing various phenomena. So he rewrote what we knew about electricity and magnetism in this language of calculus. And then he did something kind of amazing, which is he started to do math on the equations. That is, once he had the laws sort of in this symbolic form, he could start doing things to them. I want to say manipulating them. And like, really look at my hands, because when mathematicians talk all the time about we're going to manipulate equations, but we don't think of it like this. We think of it like, I'm going to take this equation and substitute it into that equation, or cancel 2 from both sides. But when you go, if you have a crick in your neck and you go to a masseuse, she will manipulate your neck with her hands, right? It comes from the word for hands. And so to us, it feels very palpable when we have equations that we can manipulate them, we can massage them, and it's almost like we're trying to do the same thing. We're trying to get them to relax, to release their secrets. Like loosen up and talk to me. And sometimes the math will do that. And so what I'm really saying is that Maxwell did some calculus operations. You don't need to know what they are, taking derivative of this. Actually, take the divergence of this side and the curl of that side and whatever. So he's doing certain manipulations on the equations. And then he substitutes one into another. And pretty soon, he doesn't know what he's looking for. Remember, he's trying to release the secrets, but he doesn't know what the secrets are. He keeps trying. And eventually, he sees an equation that he didn't expect, that is the logical conclusion of the equations that were coming from physics. And that new equation he recognized, because it's the same equation that describes how water, like if you have a ripple on a pond, how that ripple will travel as it spreads. He discovers a wave equation in electricity and magnetism. And he didn't know there was going to be a wave equation there. And this wave equation, of course, when something's traveling as a wave, you'd like to know how fast it goes. He plugs in certain numbers known for electricity and magnetism, and finds that these electromagnetic fields, as he starts to call them, the combination of electricity and magnetism, propagate at a speed that he was familiar with, because it was the speed of light, and that had been recently measured. So this was a big shocker. This may be one of the great aha moments in human history, that Maxwell discovered what light is. People had seen light since the first time we opened our eyes coming out of the cave, and nobody knew, what is this thing, light? What is light? Ask that if you're a little kid. Daddy, Mommy, what's light? Nobody knows how to answer the little kid. Maxwell could answer. It's an electromagnetic wave. Doesn't help to tell the kid that, but okay. So, but anyway, that turns out to be the true answer. Light is an electromagnetic wave, and traveling at the speed of light, it can go through empty space. And this is a prediction that came out of calculus in its manipulative mode, working on calculus in its linguistic mode. In other words, the physics was translated into the language of calculus. Then as a system of logic, divergence of this, curl of that, calculus worked on those equations until it said electromagnetic waves should exist and they should move at the speed of light if the universe is logical. Okay, and that was a prediction. So he predicted electromagnetic waves, and sure enough, in just a matter of a few decades, they were detected experimentally by Heinrich Hertz. And then just a short time after that, they were used by engineers to do something quite practical. You could wirelessly transmit energy at the speed of light. You could harness these electromagnetic waves for something practical. You'll recognize this name Tesla, since he got a car named after him. Now he's become a very important person, but he was an important person back then too. And then it was only a very short time after that that Marconi was sending telegraph messages across the Atlantic wirelessly. And very quickly, you have radio and television and cell phones and, my wireless microphone and everything. So this, I think, is a nice example, because it shows calculus couldn't do this by itself. You needed inventors like Marconi and Tesla. But on the other hand, calculus said this should be possible, combined with physics. And so this is the role it often plays. It's like a supporting player in a movie where you don't notice this player, but that person is helping the movie be a good movie. And it's always there. The calculus has done this over and over. It's not usually the star, but it's always there. So some of you will have this t-shirt or ones like it. This is a common nerdy t-shirt. That's pretty accurate. And God said Maxwell's equations, and there was light. So what you're seeing in that, those equations, the various symbols, we've got various things here, D, B, E, and H. These are fields. These are the electric and magnetic fields. These symbols with the upside down triangle, those are calculus operations. I mentioned divergence and curl. That's what those are. What they have to do with is how do the magnetic fields and electric fields change as you move around in space? Like you saw, the iron filings were changing direction. This is kind of encoding that in a more sophisticated way. And then it relates how the magnetic and electric fields change in space to how they change in time. You see this little letter T here, that's time. And so the rate of change of this field is in time is related to something about this field in space, and so on. Anyway, those are the four equations I was talking about that encode what was known about the physics of electricity and magnetism. And then by combining them in an ingenious way, Maxwell got this prediction of electromagnetic waves and light. So just to sort of summarize this first part of the argument, why calculus matters then is that it's not just about geometry. The laws of nature are written in calculus, and not just the laws of electricity and magnetism. If I had told you the same story about laws of motion from Isaac Newton, that would be calculus. If we talked about the laws of how things stretch, the laws of elasticity, calculus. Or how air flows over an airplane wing, or water flows through here, down here in the Providence River, or blood flowing in your arteries. It's calculus all the way. That we find this over and over, that whenever humanity learns some new part of nature, it's describable with this same language, the language of calculus. So there's that. And even, by the way, in case you're saying, oh, but what about quantum mechanics? I heard that that's a whole new thing, and that classical physics is boring, and I should be bored until I get to quantum mechanics, then I'm supposed to be excited. Don't have that attitude. First of all, calculus is not boring, and you're going to need it in quantum mechanics because it's true that particles don't follow the classical trajectories that Newton said in quantum theory. They're described by probability waves. But still, if you ask how do those probability waves change in time, there's a calculus equation that tells you, called the Schrödinger equation. So even though classical physics doesn't work at the quantum scale, classical mathematics still does in the form of calculus and the Schrödinger equation. So anyway, so calculus keeps working even when the physics starts to get, all right, you got my point there. So, but anyway, the second point is there's a temptation to say, oh, well, math is just a language. And yes, it is, but it's much more than a language. It always ticks me off a little when I realize people are trying to make it seem less threatening. Oh, it's just a language, so therefore it's not so scary and I can learn it, just like I could learn Spanish or something. But calculus is much more than a language because it's a system of reasoning too. That's what I was trying to drive at when I spoke about the manipulative function of calculus. And the really spooky part, that the logic of math somehow matches up to the way the universe unfolds. That what we can predict with logic is actually seen when we make measurements. Why should the universe respect our logic? That's not an obvious thing, but it does over and over. It's an uncanny thing that it does. So anyway, it's a system of reasoning somehow quite profoundly and mysteriously mirrors how the universe works. And so by learning to speak this strange language over the course of about 2,000 or maybe more like 2,500 years, and by discovering that it expresses this hidden logic in nature, we've been able to use calculus to remake the world. That's my main point. And so, sometimes they say when you're giving a talk, you should kind of get your point out early because people lose interest and attention. So I'm kind of done now. But now I'm going to elaborate, but you've got the main point now. All right, so the rest is to flesh it out and see if I can convince you that this is really true and not just hype. Okay, so in this next phase, let me try to pretend that calculus is a person. I think it's helpful to think of it that way. It's not really a person. It's a subject, an abstract discipline, but so if you prefer to be more literal about it, what the practitioners of calculus want. So what do we want when we do calculus? We want to make hard problems simpler. And that might come as a surprise if you've been told calculus is a super complicated, difficult subject. It seems like it's all about complexity. It's not. It's about simplicity. It's about making complicated things simpler. And it has a certain strategy that was the key to its world-changing powers. So here's how it gets what it wants. It takes a hard problem and slices it into smaller pieces. Now that in itself is not a big shocker. Anyone who's good at solving problems knows it's good to break a problem into smaller problems, you know, divide and conquer. So any good problem solver knows that. But calculus has this maniacal strategy where it says, I'm going to keep doing that again and again and again, infinitely. That's the new move. Don't just divide the problem once, divide it infinitely. That is a big idea, probably the single biggest idea at the heart of calculus. I'm going to call it the infinity principle. It's a made-up term. No professional mathematician in the room will even know what I'm talking about, except they do, because we all do know this. We don't have a name for it, and I think we're making a mistake as educators by not bringing it out. There's one theme that runs through the 1,000-page textbook. It's not derivatives and integrals. Those are subordinate to this bigger theme, the infinity principle. So I think we ought to just shout it out from the rooftop. And so here's what the infinity principle says. That we're going to keep slicing and slicing problems ad infinitum. In other words, we're going to take something and chop it in half, say, and in half again, until we get infinitely many pieces that are now infinitesimally small. And the reason for doing this crazy thing is that it's going to turn out that solving the problem for the infinitesimal pieces will be easier, much easier than the original question. So that's good. We'd rather do an easy problem. That's what I mean by calculus making things easier. You're going to solve those easy small problems. The part that's hard is putting the answers back together to answer the original question that you cared about. And so calculus then naturally divides into these two halves that you've heard of. The slicing half we call differential calculus. It looks at the difference between the pieces. And then the hard part is integrating the answers back into the whole. The rebuilding part is integral calculus, and that's always at the second half of the course. Students find that part harder. It is harder. All right, so let me bring out, though, that this whole strategy that runs through all of calculus is predicated on a big assumption that we can keep dividing things smaller and smaller forever. And the jargon is such things are said to be continuous. So, well, you know, what things in the world are continuous? That's the problem. Nothing. There's a big act of creative fantasy here. That calculus is a model of reality that is actually not really literally correct, but it's enormously powerful and works well. And so it's like art. I'm going to argue that there's a connection to art here, where you don't take a photorealistic picture of the world. You take an impressionistic painting of the world that teaches you a lot of the truth, even though it's a little bit wrong. So, I mean, maybe in case that's not obvious what I mean. So, like, think of ordinary matter is, what's that strange noise? I don't know. Something's doing the wave equation and making sound waves. Is it me? No. Okay, if you'll ignore it, I'll ignore it. Okay, anyway, so continuous stuff. So like, let's suppose I have a loaf of bread. You know, you might think, well, that may not be good because that's a lot of holes in it, doesn't it? How about, what seems continuous to you? Water? The wall? Okay. So, yeah, I mean, that's, what I want to do is start chopping something, so the wall is a bit of a chore. How about...
A length of rope.
A length of rope would be okay. Yeah, okay. Yeah, okay, rope. So I could cut the rope in half and half and half, and at some point, I mean, if I do it a lot, I'm down to the atomic or molecular scale, right? And I'm going to have trouble cutting the atoms in half, and maybe if you think I can cut them in half, still going to be hard to cut the proton in half. I mean, at some point, the graininess of nature is there. The physicists tell us that nature is made up of particles. And so we don't really believe anything is continuous all the way down. At some point, calculus won't. It's making a wrong assumption. And yet we're going to ignore that. We're going to just pretend we can imagine water or silly putty or rope to be continuous. That the whole subject is predicated on that. Similarly, there are times when calculus is used in biology, let's say, to study something important like the level of virus in the bloodstream of a patient with HIV. All right, so there are billions of virus particles before the patient is treated with the drug cocktail. And we want to study the progression of HIV, and if we can, you know, suppress the production of these virus particles. But keep in mind that they're particles. They're discrete, yet we describe them with continuous calculus equations. And yet, that's the best thing we can do. That really works, but it's not quite right. Okay, so that's the creative fantasy behind calculus, and so I'm going to define this whole subject as this creative use of the infinity principle to shed light on anything that's plausibly modeled as continuous. Any shape, any object, any motion, any process, any phenomenon, anything that can be treated as continuous is grist for calculus. So let me give you an example of this going back to really like middle school, in case you haven't run into these ideas before. And it has to do with the age-old question of the area inside a circle. So I'll just remind you, circle has a diameter, the distance across at the widest point. That's twice the radius. That'd be the distance from the center out to the circle. The circumference, the distance around. And so we all learn this formula that the circumference is pi times the diameter, this magical number pi, the ratio of the circumference to the diameter, pi around 3.14, et cetera. That's already a clue something funny is going on with circles, right? That as little kids we learn about pi. It's this amazing number. It's got infinitely many digits. They don't repeat. Little kids like to memorize the first 20 or 50, depending on the nature of your child. Some are not interested in memorizing. But still, pi is already a signal that infinity is involved somehow in circles because it's got this infinitely many digits that follow no obvious, in fact, no pattern that we know of other than that they're the digits of pi. Okay, so there's pi, this relation between the, so that has to do with the distance around the circle versus the distance across. But what if we want to know about the area inside the circle? Okay, so here's an argument I want to show you that gives us the formula that the area of a circle is pi r squared, something that everybody memorizes for their SAT. R, the radius, pi, the number I just talked about. Where does this formula come from? So I'm going to show you an argument for this that uses the infinity principle. And if you've seen it, I hope you still enjoy it. If you haven't seen it, prepare to have your head explode. So, okay. So here's the strategy. We're going to pretend the circle is, think of it as a mathematically perfect pizza. It's perfectly round. It's got an infinitesimally thin crust. I'm going to cut it into 4 pieces and then rearrange the pieces. And the strategy is to make it into a shape whose area I know. Because if I can make it into a shape whose area I know, then I will have figured out the area of the circle, because all I did was rearrange the pieces. So in the first attempt, we take the 4 pieces and rearrange them to make that funny shape there, which looks very unpromising, like you've made the problem worse. This does not seem to be helping. And that's true. We have made the problem worse, but that's in the nature of drama. If you watch a play or a movie, often the character has to get into trouble before getting rescued and something happy at the end. So we're going to do, that's the character of this proof. There's the radius of the circle. I'm going to just highlight that again. There's r. That's one side of the pizza. And then I've indicated that the curvy part has a total length pi times r. So just to remind you why, if pi times the diameter is the circumference, then half of that, half the circumference is on the bottom here, and the other half, the circumference, think of it as the crust, is on the top. So we've got half the circumference on the bottom, and I said the circumference is pi times the diameter. So half of it would be pi times the diameter over 2, which would be pi times the radius. Or if you're remembering 2 pi r as the circumference, then half of it is pi r. Okay, so just make a note of those 2 numbers because they're going to be in all the pictures. Now, as I say, I've made the problem worse, but that's because I didn't take enough slices. So the brainstorm is, what if we made 8 slices? Then we have that, we rearrange them up, down, up, down, up, down, and now this shape is starting to look a little more recognizable, right? Maybe anyone want to, do you mind if I pick on you? Does this shape look like anything? Do you know a name for a shape like that?
A rectangle.
Looks almost like a rectangle. Looks a lot more like a parallelogram. Thank you. So parallelogram, because this side is parallel to that side, and this sort of looks parallel to that, except it's not really a parallelogram because this is not flat, right? These are curvy still. But let me compare. You know when you go to the optometrist, they will sometimes say better, worse. I'm going to do that with you for a second here. Okay, better, worse, better, worse. So can you see that it's getting better? What do I mean by better? It's a little bit flatter. And notice another thing, that the tilt is less. Because you said rectangle. It's going to turn into a rectangle. And to make it a rectangle, this tilt has to be vertical. So watch it got more vertical. Do more. Now with 16 slices, you have that. And it's starting to really look a lot like a parallelogram. Notice it's hardly bumpy at all. Meanwhile, it's always r on this part and pi r on that part. So if I do this ad infinitum, that's what I said was the big move in calculus. What I really want is infinitely many, infinitesimally thin slices of pizza. If you did that, you get that. I can't show them because they're infinitesimally thin, but I hope you can see that's the limiting shape. You know, again, doing my optometrist thing between that and that. Notice it's standing up straighter and straighter, and it's also getting less and less curvy on the bottom. So hopefully you find it plausible. This is a part where it's not really a proof. I mean, you have to reason more carefully if you wanted to satisfy a certain type of mathematician, but I hope, you know, commonsensically it's clear to you that this is approaching this limiting shape. And so now we can just say, well, I know the area of a rectangle, it's this distance, that distance. Pi r times r, that's pi r squared. And that really is like 99% of the truth of why, you know, leaving out some technicalities. That's really the reason why the area is pi r squared, because a circle can be rearranged into a rectangle. So what's the lesson there? That with the power of infinity and this infinity principle, we took a problem that was mystifying and made it much simpler. Made it very easy, in fact, through a very ingenious use of infinity and infinitesimals. So this is what now this kind of argument is thousands of years old. This was known in civilizations around the world. They discovered it in Japan. Archimedes had a version of it in Greece. So it's like the Egyptians have a version of it. There's ancient Hebrew scholars who found it. People found this all over the place. Okay, so that's an example of calculus in the service of understanding something about a curved shape. Maybe I should say, actually, before I go on to this 3 big obsessions, you know, just running back to the circle. Like, who cares about a circle? Why did anyone ever care about that? You could say, well, you know, was it some practical thing because the wheel was important? We needed to know the area of a... I don't think so. I think it's a case of pure human curiosity and desire to understand a shape. That the circle, you look at someone, you see circles in their eyes, right? They've got a circular pupil. You look at the moon, it looks kind of circular. People came up with the abstract idea of a circle from observation and then wanted to know, just like they did need to know what the area of a field was to know how much tax to impose on it. Okay, they weren't imposing taxes on circular fields, presumably, but they just got curious. I don't know, I'm making this up, but we don't know why people wanted to know the area of a circle, but they did. And it took really hundreds and hundreds of years to figure it out. Why? Because curved shapes are hard. That's the first point I want to make. Curved shapes are hard in a way that in a way that rectangles and triangles are not hard. Things made of straight pieces that's what you learn about first in geometry. And if you look at Euclid's classic geometry textbook, it's filled with problems about shapes made of straight lines and flat planes. Those are easy. It's things made of curves that are hard. And why are curves so hard? Because they don't have any straight pieces in them. Okay, they're just different. There's nothing to latch onto. And so the great imaginative move in calculus is, let's pretend they are made of straight pieces. They're not, but let's pretend they are, right? So we kind of did that with the circle when we looked at it as almost looking like a rectangle made of lots of triangles. Anyway, so trying to understand curved shapes was a big obsession of calculus, its first big obsession. And so, but then there were more. Obsessions had to do with understanding motion, how things move on Earth and in the solar system, and more general kinds of change, like I talked about the changing levels of virus in a patient's blood, or it could be you know, changes in the economy if you want to get really modern, or you could think about anything that's dynamic is what calculus is concerned with. You could even think of, I mean, if you had to say what calculus is in one word, I would say the word would be change, the mathematics of change. Because that actually applies to curves, because what makes a curve curved is that the direction is changing. So curves are about changes in direction. Motion is about changes in position. So it's all change, really. Just anything that can change, that's what calculus wants to know about. But specifically, continuous change, not jumpy change. Okay, so curves was where it all started. And I want to give you an example of another magnificent argument, going back, to the ancients, just because these are kind of elementary, and I think they make the point more clearly than the more technical modern stuff. So here's the way that people used to think about curves in Greek times. You would take a circle, make a shape out of it called a cone, where the circle shrinks and comes to a point. And then if you cut the cone at an oblique angle like this, you get a shape that we call an ellipse nowadays, a certain kind of oval shape. But in the old days, it was regarded as a conic section, meaning what you get by a section, a cutting through a cone. If you cut it at this kind of angle, you get an ellipse. If you cut it at an angle parallel to the side of the cone, you get this other shape, a parabola, which you'll know from parabolic arcs of water coming out of a drinking fountain, or we see parabolas all over the place. But anyway, that's how you could make a parabolic curve, cutting a cone. And so Archimedes, around 250 BC, was really the first person to tackle the mystery of curves using calculus. You won't find calculus in Euclid, not really. I mean, Euclid doesn't have pi r squared in his book. He doesn't even have pi. The first person to really come to grips with pi in a serious mathematical way is Archimedes. But so he's also tackling other curved shapes like parabolic segments, where you take a parabola and cut through it at this oblique angle that I'm showing. And his question was, what's the area enclosed there? What's the area of that parabolic segment? So Greeks are all about proportions. They loved phrasing things in terms of proportions. And so Archimedes is going to tackle the problem as a problem of proportions, but he does it using what he knows, which are triangles. And to me, this is such a spectacularly imaginative, out-of-the-box thing, to see that curved shape as being made up of triangles. That he's going to put a triangle inside the parabolic segment, a big one, and then in the remaining space, he can sneak in another triangle and then another one in here. And then you see there's a little white space left over. And he could squeeze in some more triangles there, and he's going to squeeze out, or the term that was used is exhaust. He's going to exhaust all the area using triangles. And to me, it's like cubism. I mean, it really looks a lot like paintings you see by Braque and Picasso, where curvy bodies are made up of lots of rectilinear shapes. But he's doing this 2,000 years before them. So his big result is that the area of this parabolic segment, compared to the area of the big triangle, by that I mean that one, the big triangle, the area of the whole thing under the curve is in a 4:3 ratio to the area of this triangle. That's his interesting claim. That's how he expresses the area, as this proportion. As 4 is to 3, the parabolic segment is to the big triangle. So now that would have meant something to him aesthetically. So we have any musical people here who recognize the significance of the numbers 4 and 3 for music? I'm thinking here about, okay, suppose I said, what is 2 to 1? Why is that important in music? 2 to 1 is an octave, right? If I have suppose I have a guitar string and another guitar string made of the same material, same length, everything. If I pluck them, they'll sound the same. But if I put my finger on a fret halfway up one of them and pluck them, then the long one will be an octave lower than the short one, right? That's the octave from do to the next do. Okay. So that's 2 to 1, and the Pythagoreans knew about that, yes? Is it a perfect fifth? 4 to 3. So a perfect fifth would be 3 to 2. And a perfect fifth, my musically minded daughter told me, is like going, let's see. So if we go, do, re, mi, fa, do is 1 or 0? Do, re, mi, fa, so, do, so. That's a fifth, right? Do, so. Which she told me is the beginning of Star Wars. Da, da. That's a fifth. So a fifth that's 3 to 2. If you have strings that are 3 to 2, we'll go da, da. Okay, so all the Greeks knew 3 to 2, perfect fifth. And they thought that was the most beautiful interval. But then there's another one, not quite as nice, which is instead of going up to so, you go to the note just below it, the 4th note instead of the 5th note. So let me try again. Do, re, mi, fa, do, fa. Here comes the bride. Right, that's a 4th. Here comes the bride. That interval from here to comes is a 4th. And that's a ratio of 4 to 3. So when Archimedes got this 4 to 3 result, I bet he was hysterical that that the musical harmony that's so meaningful to him, this ratio of 4:3, is right there in the geometry of a parabola. So here's his argument. He says, take the parabola, put in the big triangle. Now, how do you define the big triangle? He does it like this. He takes the base, and then he slides it up parallel to itself until it's just touching the parabola at one point. And that's what we would nowadays call the tangent line. Right? So it's just touching the circle. Tangent means touching. So it's just touching, like the word tangible. Yeah. So a tangent line is just touching at the one point, and then that defines the third corner of the triangle, so he draws that in. And then he uses that construction for the other triangles, like he's going to take this side and shift it parallel to itself until it's just touching at one point. So that gives him this. And over there he does the same thing. And what he can prove, and I'm going to skip this part, but this is where all the hard work is to show that if this is called area 1, that's the unit of area, he can prove that this has area 1/8 as much as that. That's not obvious, but it's true. Okay, so that he has to use properties of the parabola known at his time. But so you could sort of maybe believe this is about 1/8 as big as this, and so is this actually. So what's interesting is that when you create the new triangles, let's call them the daughters of the mother triangle, the daughters together make up 1/4. 1/8 plus 1/8, 1/4 as much as the mother. And that rule holds at every step because he's going to do this infinitely often. Having made two triangles, he's then going to erect little triangles on those sides and do their tangents and so on. He's going to get 4 of them, but it will still be collectively 1/4 as much as the previous. And so he's led to think about 1 plus a 4th plus a 16th plus ... out to infinity. So he's doing one of the first infinite series in the history of math. And we teach that in high school math nowadays, or maybe even middle school, depending where you are, but mainly probably high school. But anyway, he can calculate the sum of this geometric series and gets that it's 4/3. But the way he does it doesn't look like the way we teach it. He gets that it's 4/3 by this picture. He says, imagine 4 big squares, each of unit area 1. So the whole thing is 4. And then he says 1/3 of that is occupied by 1 plus a 4th plus a 16th plus a 64th, et cetera. That 1/3 of the 4 is the shaded area. How do I know it's a third? Because look what's above it. It's the same thing. A big square, a 1/4 of a square, a 16th of a square, and so on. And the same thing is over here, a 1 plus a 4th. You could put those 3 things together to make the whole 4. Isn't that a great picture? So that's a really nice proof that it's 4/3. Anyway, so he has that proof. And what's really great about it, I mean, for a technical person who might like this, he doesn't do the ... He actually does what we would call the finite sum, because he can sum up to any place he wants and then stop, and he knows what the error is. The part that he hasn't included is this tiniest little square at the top. So he knows exactly how much error he's making if he stops at any finite place, and he can see that that's going to 0. So anyway, he's a very smart dude, Archimedes. Okay, so again, notice that we're using infinity to solve this interesting problem about the area under the parabola. Okay, so you might think very esoteric, who cares about the parabola? Here's my point. This idea of approximating something like a smooth-shaped parabola or its segment with lots of triangles is an idea that lives on today. Here's an approximation of a mannequin's head with triangles that you make successively smaller and smaller, and pretty soon starts to look like a smooth face of a person. And where do we use that? Well, we use it in places like this. If you look at this movie, Jerry's Game, that got the Academy Award in 1998 for Best Short Film, Animated Short Film, it's full of polygons. This was the first movie that had there was an animated movie whose main character was a human being who was emotionally expressive. Toy Story was earlier, but those were toys. You know, like Woody's face doesn't really move. It's made of wood. Moves a little bit. This guy's really expressive. And getting his, his wrinkly neck and everything just right was a big triumph of computer graphics, but it was using this Archimedean strategy of using triangles to approximate smooth surfaces. And, when we see movies we may be more familiar with, Shrek explaining to Donkey that onions have layers, his little trumpety ears or his belly, there's millions of polygons in there that have been animated and, can convey all these different textures of the two very emotionally expressive characters. So there's that. I mean, we're using this technology all the time nowadays in computer graphics, but we're also using it in medicine. So here's a case of a guy who you may notice his chin is sticking out a bit. So he has a kind of a malformation in his face that's causing him not just cosmetic problems, but medical problems. It's not good. And so he wanted and did have facial surgery. But you know, when the doctors have to think about what they're going to do to try to okay, I mean, you can see after the surgery he looks like this. So they were able to give him that chin instead of that chin. But what does calculus have to do with this? There were mathematicians working with doctors in Germany made what was kind of like a flight simulator for surgeons. They could make a virtual patient in the computer that the surgeon could then do a virtual operation on and ask, if I cut out these bones and then reattach, what will the patient's face look like after he heals? That's what you would want to know, because that's what you'd, you know, to decide what you're going to cut. You don't get a second chance. You want to do it right. And so they made a big mathematical model of the man's face using elasticity of skin, you know, all kinds of parameters about how skin will deform. But also they have to think about the bones underneath. So they did a big scan of him in a medical scanner with millions of points. And also keeping track of all the soft tissue behind the face, all the cartilage and tendons and blood vessels and everything else. Very complicated problem in what we would call continuum mechanics, you know, to approximate all these tissues. But so with this model, they could then predict if we make these cuts and sew the guy back up, his face is going to look like this, whereas before it looks like that. And so then you can compare the prediction to what his face actually looked like after the surgery, and it's pretty good. I mean, they quantified it. If you look in my book, I give the reference, and you can see that it's not just a visual thing. This really does work and has been a very important improvement in the way we do certain kinds of surgery. But what's it have to do with calculus? Well, the model is based on Archimedes' idea, among many other things. They make these triangulated meshes of the person's face, but not just the face, but also the soft tissues are modeled with tetrahedra, three-dimensional versions of triangles. And they calculate all the forces as all the tetrahedra deform and pull on each other after the surgery, and try to figure out when the face comes to equilibrium, meaning when it heals, what's it going to look like. It's a massive calculus. And I mean, at ICERM, of course, doing a lot of computation here, it's the kind of thing that's perfect for the use of computers combined with calculus, combined with mechanics and doctor work. And so you can see, again, calculus as a supporting player in a very real world thing. Okay, so let me leave you with just zooming now to the present, just to give you a little taste of what's happening today. 1800 years after Archimedes, calculus starts to look like what we recognize today because it has algebra in it. You know, Archimedes doesn't have algebra. Algebra gets invented. I mean, the Greeks have a kind of algebra, geometric version of algebra, but the algebra we know of with symbols, y's and x's, is a creation of like the 1500s in Europe. But even before that, it's in the Arabic world and in India, you have people starting to do the first word problems and questions with unknowns in them, and manipulating equations and all that. At first it was mainly with words and sentences and paragraphs. It became symbolic. At some point after algebra, which you could recognize as an Arabic word, right? Algebra it is an Arabic word. Anyway, algebra from like 800 or so in Baghdad, in the work of Al-Khwarizmi, who gives us the name algorithm. You know, anyway, all this stuff is happening in the Middle East after, at this point, Europe has kind of gone into the so-called Dark Ages, but it's going great guns in Baghdad. It's not dark there. They're inventing algebra and doing a lot of other fantastic science. And that stuff then makes its way to Europe in the medieval period. And by around the early 1600s, you have people in France like Descartes and Fermat having the great idea to combine old school geometry with the newfangled y's and x's coming out of algebra. And so they do the kind of thing we see in high school, I guess be analytic geometry or pre-calculus or algebra 2 or something. You graph equations like y equals x squared, and lo and behold, you're getting classical shapes like the cuts of a cone, the conic section, the parabola, coming back as the graph of an equation. And so it can now be analyzed with new techniques, And again, the infinity principle is the key thing. If we wanted to ask, how could I find a tangent line to a curve? You know, like we saw Archimedes needed to do in his work. To find a tangent line, we're going to zoom in on a point. Like if I zoom in where that dot was, the curve starts to look straighter, kind of similar to how the circle began to look straighter and straighter when we made the slices smaller. If I zoom in on that dot, so notice it's at 0.5, but this is going like 0.4 to 0.6, and here it's at 0.5 squared, that's 0.25. If I zoom in even farther, it really looks straight. It's not perfectly straight, it's still a piece of a parabola, but notice the scale is much smaller now. It's 0.5 going down to 495 or 505. In the limit of doing this, zooming in sort of as fine, as close as we want, we get the feeling that curves are made of infinitesimal straight pieces. And that is essentially what's going on. That's the key idea behind differential calculus. And you know, this concept that if you take calculus, the first thing you learn is the derivative. You notice I didn't really start with the derivative. This is where the derivative comes into the calculus story. It's only at the beginning of the 1600s in the work of Fermat and Descartes. By the way, you might wonder, how come I didn't talk about Newton and Leibniz yet? Everybody's always taught they invented calculus. Well, not by my definition. Not if you think the infinity principle is the heart of calculus. It was going for 2,000 years before Newton and Leibniz. But they did make it into a system and made it much more powerful than it was. So they get credit for that. But anyway, just to finish here, so what does this gain for us, knowing that curves are made of all these little straight pieces? When we try to analyze problems that go beyond curves to things that are moving or changing, which is really what we care about nowadays, this concept of derivatives and related ideas, differential equations, give us, like I say, the modern world. So just to give you a taste of the kind of question that we can answer with calculus, let me show you something having to do with the great runner Usain Bolt, because I want to talk about velocity, which is a kind of derivative. It's a rate of change of position, or distance down the track with respect to time. And we're going to use curves to analyze this. Now, so you probably all know Usain Bolt, but at one time the world hadn't heard of him. He was mainly known for running the 200-meter dash. You know, he's a sprinter from Jamaica, very tall actually, 6'5". That's unusual for a sprinter to be that tall and gangly. Usually sprinters are compact and very muscular. He was kind of tall and skinny. And people said, you're not going to be able to run the 100 meters. That's not a good race for you because you're very slow starting compared to these best runners in the world. But he wanted to try it. And so he ran the 100. He got his coaches to agree. He started pumping up with weights and he made himself more muscular. And he had only run the 100 meters 5 times competitively when he went to Beijing in 2008. So he was a beginner at this race, but he was good, as you'll see. And so I'm going to just show you the clip of him running the 100 meters on a night in Beijing that the world will never forget. Okay, so let's see here. Hopefully this will work.
And so back to 2008 and the Olympic Games in Beijing, the final over men's 100 meters. Usain was ready to do his thing.
And they're off. Great start by Richard Thompson in lane 4 from Trinidad, and here comes Usain Bolt. Bolt is pulling away. Bolt's looking back. You don't look back in 100 meters. 9.68 is a world record for Usain Bolt.
9.68, a new world record, the fastest man in the world. That celebration on the line told the world he could run faster, and soon he would. But it was the Olympic gold medal he really wanted.
All right, so I heard a couple of people snickering. You saw that thing he did right at the end? Watch this again if you didn't catch it. It's amazing what he does. So, of course, the announcer says you don't look back in the 100 meters. There's no time. But he's so far ahead that he actually does a chest thump. You see him doing that? He's thumping his chest. He's got clear daylight between him and everybody. Just show that from here. Wait. Notice his arms are down. He's totally broken form. He's celebrating. With 20 meters left, he's so far ahead, he's celebrating.
Bolt's looking back. You don't look back in 100 meters. 9.68 is a
that separation of the line told me he could run faster. And soon.
All right, so there's a nice clip from right at the end where you can see the daylight between him and everyone else. And these are good runners. Now, I don't think you can see it from where you're sitting, but I can see it from here. His shoelace is untied. He's just very relaxed. So the question arose, if he had run hard all the way to the end and didn't fool around, how fast could he have run? It's a very natural question, right? He already broke the world record goofing around for 20 meters. What if he ran his fastest? So that was the question at the time. What would the theoretical world record be if he ran hard? And so we could take data from his race in Beijing, where what's being shown is the time at which he crossed the 10-meter mark. They have so-called split times. They had cameras every 10 meters. And so we know where he was at 10 meters, what time it was, and what time it was when he crossed 20 meters, and so on. And then you can connect the dots, and you get his position versus time. Now, when I say connect the dots, I've connected them in a certain way here. And so we don't have the data in between the dots. We don't know where he was. But I've connected them with a smooth curve that is flat at the beginning. And I know that it should be flat because that means he has no velocity initially. He's not running when he's in the blocks. He started at 0 speed, we know that. So whatever the curve is, it should be flat at the beginning, and then it should go through the dots. And there are techniques for how to draw smooth curves through dots, using calculus, by the way, and statistics, that there are various ways to do it, but this is a reasonable way. So drawing this smooth curve through the dots, you can then ask what's the slope at each point on that curve, and that slope will tell you his speed at each moment. And so from this attempt to draw the smooth curve, you can see that his speed starting from 0 goes up to, I mean, up here he's going about 23 miles an hour. It's like a little under 12, something like 12 meters a second. And but then here, you'll notice he starts slowing down. That's what we saw. When he started fooling around, he did this at the 80-meter mark or so. So that's the question. If that were just extrapolated, how fast could he go? Or what would his time have been? Well, we didn't have to wait long because the next World Championship was just a few months after the Olympics, and it was in Berlin. And people went with laser guns, you know, like the police would use, like a radar gun to see if someone is speeding. They put little dots, reflective dots on the back of all the runners, and then they were shooting these laser guns at them so they could measure their speed and position about 100 times a second. So very nice measurements. And so this is what they measured for Usain Bolt in Berlin, where he again broke the world record, his own record, and ran something like 9.58 instead of 9.69. And, there's an interesting thing that happens in this data. So here's his velocity versus time again. Notice it's not dipping at the end. But I'm showing two curves. One is the average speed, you know, kind of like the simplest smooth curve through there. This is not my data, actually. A team of German researchers collected it. But so they did this trend line, the dashed line. But then the actual data is this wiggly line. Does anyone understand why the data would be so wiggly? Anyone want to take a guess at that? Oh, you want to tell me? You're doing something with your hands. Can you just do it high so everyone can see what you did?
Because of his gait.
It's because of his gait. You're seeing his individual footsteps. His velocity changes. When he puts his foot on the ground, when he lands, he slows down a little bit. When he propels himself up and leaps, which is what running is, leaping and landing, he's a little faster. So you're actually resolving. He runs 41 steps, 41 strides in a race every time in the 100 meters. The other guys do 44 because he's much taller. So he does his 41 strides, and you could count them. But those oscillations are his individual strides. And I want to end with that because I think it's an interesting metaphor for what we're talking about tonight, which is, I said calculus is a model where it pretends that things are continuous. But if we start looking down at the atomic scale, you know, our theory will start to break down a little bit. And here's a case where if you resolve too much, like I think these laser guys with their guns, they're picking up interesting information, but it's not really what we care about. You're now seeing individual gaits. We really just wanted to know how fast he could go. And I think it's a case where we sort of have too much information, and we're losing the smoothness of the curve in favor of this wiggly curve that we don't care about. So I just want to leave you with this quote from Picasso, that art is a lie that makes us realize truth. I think there's something similar happening with the application of calculus to nature, that it is a kind of lie to pretend things are continuous, but it's such a good lie that it really helps us learn the truth about the way the world works. Okay, thanks.
So we probably have some time for a few questions.
Great. Okay, please.
I want to hear about the Declaration.
Oh, yes, of course, the Declaration. All right, so I'll try to make it fairly quick. The short answer would be that the Declaration is a product of Enlightenment philosophy, about human rights from work of Rousseau and, well, especially John Locke. And so these people were all very much influenced by Isaac Newton, and his laws of nature influenced the writing of the Declaration. That's the short version. If you want me to really make the case, let me just try. I don't want to go on too long. So I. Bernard Cohen, who's a historian of science, makes this argument in his book, Science and the Founding Fathers, how science influenced a lot of the founding of the U.S. with people like Ben Franklin and Jefferson. So first of all, Jefferson used some interesting phrasing. He says, we hold these truths to be self-evident. Right at the beginning, right? The famous preamble. We hold these truths to be self-evident that all men are created equal, etc. And self-evident has a very specific meaning in math. We hear that when Euclid begins the elements, that's supposed to be the foundation of geometry, he lays down what he calls the self-evident, they're axioms. These are the things that are so obvious, we can't possibly doubt them. We start with the axioms, then we use logic and build a sequence of propositions that carries a lot of rhetorical force because we've used logic. So if the propositions follow logically from self-evident truths, they will be true too. That's the point. And that style of argument, the Euclidean style, is what Newton used in the Principia. So his great book. He uses the Euclidean framework of deductive reasoning from self-evident truths. And so we know that Jefferson wanted to give his argument this feeling of being inevitable and inescapable. If you accepted the self-evident truths that all men were created equal, that they're endowed by their creator with certain inalienable rights, etc., you had to accept the proposition that the colonies had the right to separate themselves from this tyrannical king. It was the way that learned people tried to argue most persuasively at the time by using geometry, this style of Euclidean argumentation. And so they all knew this style of reasoning. Spinoza wrote a famous book about ethics around earlier than the Declaration of Independence, but in Spinoza's book, the subtitle is Ethics Demonstrated in Geometrical Order. He tries to use this same style. So it was a commonplace style, and just to further drill in the point, and I think I probably made the point, but Jefferson had a real fetish about Newton. He had a death mask of Newton, which is a creepy thing that we don't know about anymore. But when people used to die, they would put I don't know what, some kind of impression, a wax mold or something on their face. And then you now have, this is what Isaac Newton looked like when he was dead. And you could have that for fun. And so Jefferson had a death mask of Newton that he enjoyed. I don't know what he did with it, but he he had it. He had a death mask of Newton. And then when he was no longer president, he was corresponding with his old, sometimes friend, sometimes enemy, John Adams, about, hey, what's it like? You're not president anymore. Yeah, no, I'm not either. What are you doing with yourself these days? And so there's a quote that I quote in the book where Jefferson says in a letter to Adams from around 1812, I'm no longer reading the newspaper. I've given up newspapers for Thucydides and Herodotus, Newton and Euclid, and I find myself much the happier. So he really cared, he knew all of that stuff, and so I'm sure that, also the other thing is, the Declaration contains some very peculiar phrases like the laws of nature and nature's God. You'll find that interesting phrase in the Declaration. The laws of nature and nature's God, which I find very interesting, because first of all, the laws of nature was an idea that came out of Newton, and nature's God really gets me, because putting God subordinate to nature, it's not like God's natural world, it's nature's God. It's very interesting. It shows you this kind of philosophy that they had, that nature was the supreme thing in their minds. I may be reading too much into that part, but anyway, okay. So that's the argument, that I think it's in there, and it's only, you know, the power of Newton's work came from his using calculus to make this what he literally called the system of the world, for understanding how motion on the Earth and motion in the heavens, you know, of the moon and the planets, they all obeyed one universal principle that he discovered and used calculus to explain. So that's the argument for the declaration. Okay, sorry, long answer. Yeah, did I exhaust you with that answer? Maybe I did. Oh, yes, please.
So I'm curious, I'm really interested in the idea that calculus is the language God speaks. Why not say math is the language that God speaks? Why this more specific reasons, calculus?
It's a fair question, right. Why not just say math is the language God speaks? And that's probably the more defensible thing to say. Yes, but I mean it is. And people have tried to say that over the centuries. So when you see Galileo, Galileo was the first one I'm aware of he actually has this beautiful lyrical passage in one of his writings about the book, that the universe is like an open book before us. But to read the book, we have to learn to read the language in which it is written. And then he says, and the language is the language of geometrical figures, triangles and squares and things. So for him, geometry is the language of the universe. And that's because calculus doesn't really exist yet in the form that we recognize it today. But I really don't think that Galileo is right. I would say calculus is more the language of the universe than geometry or anything else, because the laws of nature are specifically of one type. They're differential equations. That's true in fluid dynamics. It's true in classical mechanics. It's true in... Okay, if someone's really specialized and knowledgeable about modern physics, you could say it's not really true what I'm saying now. That everything up to about 1920s version classic quantum mechanics is differential equations for 300 years since Newton, including Einstein's general relativity, you know, for gravity and curved space. It's all differential equations, and that's all calculus. But the argument would be not good enough now that we know about things like quantum gravity. You know, we're at the scale of the Planck scale, meaning, I don't have to get into it, but there's a reason to think that space and time will become fundamentally discontinuous at an incredibly tiny scale, 10 to the minus 35 meters or something. I mean, way, way smaller than any particle we know of. So there, calculus will not be the language of the universe, for sure. It will be graph theory or some as yet undeveloped. I mean, there are things called loop quantum gravity and string theory. They're not exactly written in calculus. They're written in quantum mechanical things that are not quite calculus. So it's not totally true that calculus is the language of the universe. But first of all, quantum gravity doesn't really exist yet as a theory. So I think we're probably okay with calculus. It's mostly true. It's like the whole thing with calculus itself. It's an approximation to the reality. But I think there's no other part of math that has a better claim than calculus. I think it's the best answer. But yeah, you could be safer and just say math. Yes?
At what point do you feel like somebody, or think somebody knows calculus as opposed to not knowing calculus?
When would I say someone knows it as opposed to not knowing it?
Yeah, so Wolf was trying to know calculus. At what point does someone know?
Wow, what an interesting question. Yeah, what does it mean to know calculus? I wouldn't want to put it as a binary thing that a person does or doesn't know it. They can know it better or better, right? That, you know, if I give them a chase problem, here are 4 dogs that start in the corners of a square, and each dog runs towards the dog, you know, next to it in the square, and always instantaneously aiming towards that dog. And as they all spiral in towards each other and collide at the center, how far do you get the picture I'm talking about? How far has each dog run as they all do? You know, if someone can solve that, they know calculus. But that wouldn't, but you know, so what would be involved in that? You'd have to be able to know calculus well enough to, okay, first of all, there's a trick way to solve that problem. But leaving that aside, you have to, it turns out they all run a distance equal to the side of the square. But even though they all make these interesting spiral paths. But if you can calculate that spiral, if you can calculate its arc length, if you can find the condition, yeah, I see you're doing it in your head. That'd be one measure. I mean, you could say a person who can get a 5 on the AP Calculus BC, I don't know. That person probably can't do my chase problem. So would I say they do? Maybe they could if they're very good. I don't know. There's no simple answer to that. Do you have a thought? Well, how would you answer your own question? No. Yeah, I mean, so I was on Science Friday recently doing an interview about this same topic, and Ira Flato said, "Is there anything in calculus you don't know, Professor Strogatz?" And that really caught me off guard, because the answer has to be yes. Of course, I mean, I don't, nobody knows everything. But I feel like I know a lot of it by now.
Okay, so if you want to learn how to do the dog problem, you should come outside.
Okay.
And buy a copy of Steven Strogatz's book. But for now, let's just thank Steven again.
Thank you.